I hat. So that means, okay, I hat will be 1, 0. This product, well, here you will get 0, and then you will get 1. You get j hat. Okay, so this thing sends I hat to j hat. What about j hat? Well, you get -1, and then you get 0. So that's minus I hat. So j is sent towards here. And in general, if you apply it to a vector with coordinates xy, with components xy, then you will get back minus yx, which is the formula we've seen for rotating a vector by 90 degrees. So it seems to do what we want. By the way, I should point out, so the columns in this matrix represent what happens to each basis vector, to the vectors I and j. See, this guy here is exactly what we get when we multiply r by I. And when we multiply r by j, we get this guy here. So what's interesting about this matrix? Well, we can do computations with matrices in ways that are easier than writing coordinate change formulas. For example, if you compute r squared, so if you multiply r with itself, well, I let you do it as an exercise, but you will find that you get -1, -1, 0, 0. So that's minus the identity matrix. Why is that? Well, if I rotate something by 90 degrees, and then I rotate by 90 degrees again, then I will rotate by 180 degrees. That means I will actually just go to the opposite point around the origin. So I will take xy to -x minus y. Okay? And if I applied r 4 times, r to the 4 would be identity. Okay, questions? Yes?
When you came out for R equals that matrix, is that like the definition of R, or is that just...
That's a very good question. So how did I come up with this R? Well, secretly, I worked pretty hard to find what are the entries that would tell me how to rotate something by 90 degrees counterclockwise. So remember, I should have said, what we saw, I think, last time or in the first lecture, is that to rotate a vector by 90 degrees, we should change xy to -yx. Okay? And so now I'm trying to express this transformation as a matrix. And if you work out, how these guys, so maybe you want to call these guys u and v, and if you write u equals 0x minus 1y, 0x minus 1y, and then v equals 1x plus 0y, 1x plus 0y. Okay, so that's how I would find it. Here, actually, I just gave it to you, ready-made. So you didn't really see how I found it. But, you will see more about rotations on the problem set. So you're going to see more about these things. Okay. So next, I need to tell you how to invert matrices. So what's the point of matrices? It's that it gives us a nice way to think about these changes of variables. And in particular, if we know how to express u in terms of x, maybe we'd like to know how to express x in terms of u. Well, we can do that because we've learned how to solve linear systems like this. Okay? So in principle, we could start working, substituting, and so on, to find formulas for the x1, x2, x3 as functions of u1, u2, u3. And the relation will be, again, a linear relation. It will, again, be given by a matrix. Well, what's that matrix? It's the inverse transformation. So it's the inverse of the matrix A. So we're going to learn how to find the inverse of a matrix directly. Okay. So the inverse of A, by definition, it's a matrix M with a property that if I multiply A by M, then I get identity. And if I multiply M by A, I also get identity. The two properties are equivalent. So that means, if I apply first the transformation A, then the transformation M, I undo the transformation A, and vice versa. These two transformations are the opposite of each other. Well, I should say the inverse of each other. Okay? So for this to make sense, we need A must be a square matrix. Okay, so it must have size n by n. It can be any size, but it must be the same number of rows as columns. And it's a general fact that, you will see more in detail in linear algebra if you take it. So let's just admit that. So the matrix M we will denote by A inverse, like this. Okay? And then what is it good for? Well, for example, the solution to a linear system. So what's a linear system in our new language? It's a matrix times some unknown vector x equals some known vector b. Well, how do we solve that? We just compute x equals A inverse b. Why does that work? How do I get from here to here? Let's be careful. Oh. Okay, well, I'm going to reuse this matrix, but I'm going to erase it nonetheless. I'll just rewrite it. So I'm saying if AX equals B, then let's multiply both sides by A inverse. A inverse times AX is A inverse B. And then, well, A inverse times A is identity. So I get X equals A inverse B. Okay, that's how I solved my system of equations. So if you have a calculator that can invert matrices, then you can solve linear systems very quickly. Now, we should still learn how to compute these things. Yes? How do I know that A inverse will be on the left of B and not after it? Well, it's exactly in this derivation. So if you're ever not sure, then just reproduce this calculation. See, to get from here to here, what I did is I multiplied things on the left by A inverse. And then these guys simplify. If I had put A inverse on the right, I would have AX A inverse, which might not make sense. And even if it makes sense, it doesn't simplify.